Hello everyone. Okay, recording this video because many of you couldn't actually make it on to the lab last Friday. So this is basically summarizing what we've done last week. Another reason I'm recording this as well is at the end of this video, at the end of this lecture, you will see a very cool trick with Prolog that can generate parse trees for natural language processing, and this would be something that you can maybe use to check different sentences of different structures, play a little bit with the grammar and so on, give you better insight on how things would work. The content we are talking about in this lecture or this lab is technically mainly just for completeness. I do not expect that you would be studying this level of advanced Prolog or would be tested with it. So just relax and enjoy the presentation there. Alrighty, so this lecture will talk about definite clause grammars. Definite clause grammars are kind of a syntactic sugar type of a trick in Prolog that can allow us to write context-free grammar in a way that we and generate the predicates that actually would make this happen in Prolog. It is basically a context-free grammar, and it uses exactly the same concepts. It is defined using this operator, and this is just for the fonts here. This is two dashes and an arrow, so it will be like this. Two dashes and a greater than symbol. This operator allows you to use context-free grammar formulation within Prolog itself. So to start off, we'll define a unary predicate. Unary meaning it has only one argument, and it is mainly just to print a list. And we'll use that to print different the results that we'll use in this lab. It's a fairly standard one, just recursing over the list, printing the head, and then doing the rest with the tail. The one with the underscore here, this is the core function or the core predicate, and the one here is just mainly um, a wrapper that can maybe add the word list here before the list and ends with equal signs here just to finish it. Alright, this would be tested fairly straightforward, and you can see the results here. This is all already known. Let's move next, which would be using string generation using DCG. So, because we want to use the double quotes as character lists, so we'll set the Prolog flag with directive here. And let's start with a very simple example of a palindrome problem. And the rules are fairly straightforward. As you know, an empty string is a palindrome. A string with a single letter is a palindrome. Anything longer than a single letter, then it should start and end with the same letter, and then the substring in between should be a palindrome. We are going to do this with several methods. First one is the normal one that we did before. So we're defining a palindrome here, predicate. What it does, it actually entails the rules that we had. Empty list, singleton variable, and we don't really care what the value is. And if we have a head, then we need some temporary tail, in which that if we append this tail with this head, it should give us the rest of the list tail. And then we need to make sure that this substring tail underscore is actually a palindrome. So this is why we check that. To test this, we're using a predicate called find n solutions, and we'll ask give us 7 solutions. This is the template. S, and then we are checking palindrome of S, and we're putting everything in a bag. And finally, we're using print list that we defined before to print the list. Alrighty, so in case you haven't noticed, maybe I need to delete that. So as you can see here, an empty list is a palindrome, singleton, it's okay. These two variables are exactly the same. These are like pointers in the memory, so if you assign a value to one of them, it will automatically reflect on the other one. And so on. You can see the symmetry here on both sides, which means our string is a palindrome regardless of what the content is. This is fairly straightforward, and this is what we've been doing before. So what's new here? There is a cool trick called tail recursion. Tail recursion is a very powerful mechanism to do recursion. The reason is it reduces the complexity from order n in terms of the recursive calls in the stack to order 1. It's not exclusive to Prolog. It's actually usually used in many other languages, and in fact some compilers in many languages do actually optimize your recursion using tail recursion under the hood. You don't really see it, but it does it this way. So the way tail recursion works is a bit mind twisting, really. What we're doing, and bear with me here, is that we are, instead of having this palindrome with only one argument, and then our base cases are actually here, we will encode these base cases in the argument list or the parameter list itself. So the way this works, we will define our palindrome predicate here with one argument. This is the input that we have, and the base case. Technically, in our problem here, we need this base case to be an empty list, right? So in that case, if this is an empty list and we'll call it with an empty list, then this should be an empty list. When we call this type of recursion, we provided an input here, and we say that we need the remaining would be empty. This remaining that would be empty also serves our base case in the recursion. Okay, so if we do it this way, now p, x, and x, saying that when we call p, x, and empty, then x should be at least empty. This is one scenario. Now, if we call p with a header that we really don't care about and a tail, we need this tail to be the same because we are calling it again with an empty. You see how it works? So basically, we are hoping that this recursion loop will lead or will yield to an empty list of strings that that remains after you process all the strings there. Now the actual recursion here happens here. So here what we're saying is, if we can split the list to h and tail, find me another base case. This is our substring, such that hopingly that this would be an empty list, and then check palindrome on this substring t and add the head at the very end to this, hopefully becoming an empty list. This is a lot to unpack. It is easier to show it in the demo though. So we'll delete this this output and we'll run that. So here the way it works is Okay, that this first one is actually not printing anything, so let's comment that. Okay, again, we're finding a solution, 5 solutions. Template is S, and then we're calling P of S and empty. So saying your base case should be empty, and we're also saying that after you process this string, the result, there should be no remaining unprocessed characters. Okay, so when we check that, it will produce exactly the same kind of symmetry in variable names, and this is our palindrome. But wait, there is more. Now let's test this with a string like ABCBA. So this is a palindrome string, okay? And we are asking what are the values of L that can satisfy, can make this one true. We're wrapping this in find n solutions. We need 5 and L and so on. And then at the very end we print the bag. Now this is very interesting. The very first answer it says here, let's run that. So the very first answer it says here is ABCBA. So if L is ABCBA, this means that it processed nothing from this string, which is still valid. If we ask for an L to have the remaining of the same string, so we haven't processed the ABCBA string at all, so we will get it at the very as a remainder. Bear in mind this is true because our definition of a palindrome accepts an empty list. So what it said is, okay, this string was like this, an empty string which we can accept plus another remainder string that we haven't processed. All right. Okay, the second option, also let's write this here. So this would be string and ABC ABC BA string equals this and remainder equals this. All right. The second case or the second scenario, which again, because our palindrome actually satisfies a single element list, whether here or we can see it in the results here, is that our string was actually A and the remainder was B, C, B, A. Now you see how this works. It tries to satisfy the condition, and from that it will give you the what the list is and what the remainder are. Okay, the last scenario, which is what we are actually hoping for, is that the actual string is ABCBA and the remainder is empty. Let's arrange this. Okay, I actually would like to save this somewhere, so I'll just remove that and perhaps this at the bottom here. Take a copy of this just in case. Let's run that again. Yeah, cool. Okay, so as you can see, the way we're doing tailor recursion here, not only is it efficient, it also gives us the remainder. And this is an important thing when parsing strings or parsing natural language in general, because your parser will try to accommodate whatever characters of words that's coming its way, but then eventually it will find something that it cannot actually process. So let's check one example here where it actually fails. For example, we have a string here A B C D C B X A. If we try this one, it should fail, and it says goal failed here because we literally specified that we need no remainders. Okay. Now, if we try another string here, A, B, C, D, C, B, A, X, Y, Z, these are extra characters that that you would that the predicate cannot actually process. So in this case, apart from the two obvious scenarios, which is the string is empty or string has one letter, the third scenario here would be the remainder, which is X, Y, and Z. Okay. Now, why we're doing this? This is important. Because we are going to do the palindrome again with the DCG syntax, and the DCG syntax is actually using tail recursion at the back end, and when you call it, you do call it with um, an empty list here to specify that this should succeed. If it gives you any remainder, then this goal should be failed. Okay, so how do we use DCG in Prolog or definite clause grammar? This is basically two dashes and the greater than, and we're using it the same exact way we're doing the context-free grammar. We're using a non-terminal here, which is P. It can go to an empty list, and it can go to a list with only a single element, and then it can go to an X variable and call itself if it has X at the very end. So this is how we define grammars in Prolog using DCG. Now, if you when we call this, we call it the same way we did the tail recursion, which is we'll ask P or palindrome of a particular string and an empty list. This is our condition for this predicate to succeed, and again it will give you symmetric pointer numbers here, as you can see. So I jumped ahead a little bit. Okay. Now, if we really look under the hood of how P was actually defined, you will find that Prolog has defined it the same way we did the tail recursion there. It uses P of A and A, similar to P of X and X that we did. If it has a single element and whatever list at the very end, we hope that this would be the empty list. And then if you have a single element and you you have a substring B, we need a list that should be empty when we call, such that that B could be a palindrome. B is our substring here, and then D should be another empty list. This D then should be mapped to the A that we stripped from the top here, and this should be concatenated to a C which we have here, and this would be the empty list that we're passing as a condition. If we passed as a variable, then this C will give us the remainder of the string that couldn't be processed. Alright, this is the old P that we defined before. This is an old P that we defined that I defined with a string there. This should be actually, it's for the text that we defined for the NLP part that we did before um, at the very end. Okay, why is Prolog actually doing it this way? The only difference between this syntax and the one we did before, which is here, is that we are actually doing the matching here in the head of the predicate. Prolog is actually doing it this way for a very good reason. Is that the case we are doing was actually the simple one. Now, if consider if we have two non-terminals, then you need to chain these, and we have hypothetical grammar here. I don't know what it does, but when we see the listing, you will find that Prolog is actually chaining this. So it's defining P the same way it does, and P again. But then because P is calling Q, then P would go to do A and C, and then takes the C, pass it to Q, and then produces D, and this D should be matching the whatever letter here and the rest, the remainder of the string. So this is why Prolog is actually using this notations that to make it a chainable way of passing different non-terminals into the same rule. Okay, so one very cool feature for DCG in Prolog is that you can wrap whatever other Prolog features into curly brackets, and these curly brackets will allow you to call for different predicates. For example, here what we're defining, you can define your alphabet. We're saying here that the alphabet is a list of A, B, and X, and our production rule can produce an empty string and can produce a string with a single character if alphabet or A, which means this A will be unified with A, B, and X, and then and X is a member of A. So this is the normal way we used to do when defining our calling predicates. And the same thing here, we're matching X and X around terminal P, but we are asserting or adding an extra safeguard here to make sure that X is a member of A, where A is actually the alphabet. So now when we use this, if we run that, it will show you all the possible combinations of palindrome using this particular um, alphabet. Alright, now let's move on to the cool part, which is NLP parsing using DCG. Now we understand how DCG works, and we understand how the tail recursion is actually being used at the back of it, and how it chains different rules together to produce the predicates to process a list of entries. Now, similar to what we've done in the lecture before, we have as a sentence could be noun phrase and verb phrase, or it could also be noun phrase, verb phrase, and prepositional phrase. And noun phrase can be proper noun or determiner and noun. Noun phrase can be determiner, noun, PP, or prepositional phrase, and so on and so on. I did a little bit of extra effort here to add to separate the verbs into intransitive verbs and transitive verbs, IV and TV. Transitive verbs are actually verbs that require an object, so you're doing something to someone or something to something. Yeah. And the intransitive verbs are the verbs that can be used on their own. So the boy plays or the boy sits and so on. All right. So basically, in the DCG here, what we have is we are defining our context-free grammar. Notice here that we defined the nouns as elements in lists, and we're using or here because a proper noun could be John or Sue, a transitive verb could be sees or gives, and so on. It's important to keep them in a list here because the DCG operates on lists, so it's expecting that your sentence is a list. Now we are finding n solutions. We are asking for 15 solutions of this particular sentence, starting with a PN, and as this could actually be S and S, and that's it. We don't really need that. Okay. And with that, if you run this, it should give you different combinations between um, of John doing different things, really. John plays, John sits, John plays with John, John plays with Sue, John plays with a dog, and so on and so on and so on. Alright, did I run this one? I don't really, can't remember. Let's just be sure and do that. Yeah. Alright. Now the even cooler part is that we can get Prolog to generate the parse tree to us. So bear with me a little bit here, and if you have any questions about this particular part, send me an email or uh, just hunt me on Teams. Um, so the DCG that we know that we used before is mainly just non-terminals going to other non-terminals, and at the very end it goes to terminals here. Okay, so that's basically as simple as it gets. Now remember when we did the AOE expert system thing, and we witnessed the trick of using tags. For example, 200 woods, we use W slash say 200, and this allows us to use say to match this with X slash Y to get the tag and the value that we want from this. Another way to actually do this tagging thing is to use functors. So what we want is um, to get PN, which is proper noun of John. Ideally, the sentence that we want to reach is when we say John plays with a dog, it should produce us a sentence of noun phrase, which a sentence of a noun phrase which is a noun of John or a proper noun of John, and a verb phrase which is a verb which is plays. And this verb phrase is a verb and a prepositional phrase which is preposition with, and a noun phrase which is composed of the terminal of a and the noun dog, and then close all the brackets. So basically we need the parser to build this parse tree from the ground up. So when it starts processing each word separately, it will place it to the right place, and start building all these brackets and functors or nested functors from the ground up to give you the parse tree. One way to do it is to use tags, which we used before. We can say, for example, s slash np, and np itself is slash n, and the n is slash John, and so on. But you see, it will start getting a little bit messier here. Another representation could be lists like s of np, and the np takes n, and the n takes John. All of this is still in the MP, and we finish the MP here, and this could be after that VP. All right, this should be here, VP, which is uh, VP, which takes a V of place, and then it takes also a PP, and so on. So this is another way to describe it, but traditionally we all agreed kind of to use this functor format. Uh, sorry, this functor format to represent the text there, the parse tree there. Okay, so how do we do that? So in the vanilla DCG or definite closed gamma, we just used these non-terminals, and we did not really pass any variables to them whatsoever. Okay, and in the next one we will actually change that, and we will pass variables, but we're not just passing variables, we are passing variables wrapped into a function or a functor. So what we're saying here is a sentence S, okay, that can take two variables, noun phrase and verb phrase, wrapped into this functor. This could be as easy as this part could be, let me copy that. This could be as simple as something like this. Okay, so instead of just using these slashes, and then we'll go into a big mess on how to decode these, we're just using the same thing, s underscore, and takes MP and VP. The use of underscore is mainly to differentiate it from the original s. In many other implementations, this should be actually a sentence, but we are trying to make things simpler. So what it says here, if I have MP and VP wrapped into an S, the S itself, the S part is useless. We don't really care about. This is just like a template for how things will come out. And then we'll check if the NP variable is actually an MP, so we'll pass it to MP, and the VP variable is actually a VP, and so on. We have the other version here. It takes noun phrase, verb phrase, prepositional phrase. Same thing, we'll check these if they are proper noun phrases, verb phrases, and prepositional phrases, and so on. I have a bit of a mess with the tabs here. Oh, okay. Now we'll go into the noun phrase. Same thing as we did with the sentence, which takes two variables. Noun phrase can take one variable, which is a proper noun, or can take two variables, determinant and noun, or determinant, noun, and prepositional phrase. And every variable you pass here, you pass it through to the proper predicate or the proper production rule in your grammar. that will check slash unify or give you what representation that can make it true. And same goes with the verb phrase, prepositional phrase, and so on. Now the alphabet or the vocabulary that we have is treated in a different way. Mainly, let me just change this. Mainly here what we're saying is proper noun is a proper noun on the I did something not correct. Where okay, so proper noun is a proper noun underscore, which is again the functor name. This is just for display. And it takes a proper noun variable here, consumes the proper noun from the list. So this will be the name in the list or the word in the sentence, which could be John or Sue. And to check that, we're using the feature of definite clause grammar here. We're using the curly brackets and asking if Pn is a member of a list containing John and Sue. Same thing here with the transitive verbs. Again, we consume the word from the list and ask if TV is a member of sees and gives, and so on and so on. Now, when we test that, we are testing S, which is our sentence, and now because we are actually using variables here, we're passing something to S, we can pass a variable here to get this this parse tree into this variable. This is our sentence. John plays with the dog, and then we are expecting no remainder here, so we are enforcing the rule that this sentence should be parsed and parsed correctly. It should be grammatically correct. So when you run this one, you will get a parse tree of the sentence. So here it says it is a sentence composed of a noun phrase, which is a proper noun, which is John, and a verb phrase, which is intransitive verb plays, and prepositional phrase, which is preposition with, and a noun phrase, which is determiner a and the noun dog. This is one way to parse this sentence, and this would be the parse tree of it. Remember in the lecture when we had multiple parse trees for the same sentence, this is where it's coming from. A second option that the system had found for us as well is actually using sentence, which is a noun phrase, verb phrase, and prepositional phrase. The one in the top here, the prepositional phrase, is actually a part of the verb phrase. That is the difference between these two. Which takes us to revealing ambiguities in parsing, and this is what we did in the lecture by hand, and this is again the same thing that you have in the practice assignment. And in this one, it's the same grammar. I haven't actually changed much. Maybe I added a couple of words to match the vocabulary there. I don't know. Yeah, other than elephant, things like that. So this one, we have a sentence here as which is John sees an elephant with a telescope. And when we try to find solutions for that, it is we call S, which is a sentence, should give us a tree, and we'll take this capital S, which has our sentence there, and we are enforcing that we have no remainders. This sentence should be parsed correctly, and then we'll write whatever the sentence is, and then we'll print list the trees. Now when we see the result here, let me clear that up. When you see the result here, you will find 3 different parse trees, and there might be more depending on how big your vocabulary is. And the main sources of ambiguity here are the use of prepositional phrase in the three parts here, which are with the sentence. Prepositional phrase could be a part of a sentence and could be part of the noun phrase and also could be part of the verb phrase. So this is where the ambiguity is actually happening with us here. All right, I will stop here. If you have, I think I finished here. Yeah, that's the last one. So I'll stop here, and if you have any questions, please hit me with an email or hunt me on Teams. This document is already up on Moodle. Have a play with it. I strongly recommend that you try the sentences that we have in the practice assignment into this system and see how different parse trees are actually being generated. There is a piece of code that can draw actually the parse tree for you, but I found that it is fairly intensive to actually go through. It's about 2 pages, and it's not really the core of our discussion. I will send you the link in the document there. Coolio. So have fun. I hope this video would actually help you understand more a little bit about the natural language processing and formal grammar theory and also prologue. So I'll see you around. Good luck with the exams. I really hope you all do very, very well. See you.